across it. So when there is a change in voltage across the capacitor, then the capacitor will then show its characteristics, which means if there is no voltage, it becomes a steady state condition, and the capacitor will not show any different characteristics. Then also, when the voltage is constant for a long time, it again reaches a steady state and nothing changes in the capacitor. But when there is a change in the voltage, then that's where the capacitor will reveal its characteristics. So capacitance can be described as opposition to change in voltage. So it means that if you change the voltage across the capacitor, the voltage will not change instantaneously. It will change slowly with time. So that's how the capacitor works. So when you are dealing with the capacitor, it stores energy in an electric field, right? And an electric field will be a region around a charged body in which if you place another charged body, it will experience a force. That becomes the electric field. So the electric field is represented by electric flux lines, which you can draw to indicate the strength of the field. So if you draw flux lines, and we are saying they will be representing the change at the density of the field, the density is now determined by the number of flux lines passing per unit area. That is what we term the density. And that density will be showing you the electric field strength. We will go into details with that. So if you have this charged body, the positive charged body there, then it radiates its flux away from itself in those directions given in the blue arrows. And the number of lines passing through a given cross-sectional area will represent the strength of the electric field, right? So for a positive charge, the flux lines will radiate outwards. Then for a negative charge, if this was a negative charge, the flux lines will be coming towards the charged body. So in other words, we are just saying the direction of the flux lines will be the direction in which a charged body would move if placed at that point. The direction in which a charged body would move is placed at that point will be the direction of the flux. And that charged body we are talking about is a positively charged body. So, as you can see, the positively charged body will be repelled by the positive charge, and hence the flux is radiated outwards. But the positively charged body will be attracted by the negative, and hence the flux radiates into the negative body. So the electric field at a point will be the force acting on a unit positive charge at that point, right? So the symbol is that E with units of newtons per coulomb, which is force per charge, or volts per meter. So you can write volts per meter or newtons per per coulomb, but you realize that we'll use force per meter in our calculations. So mathematically, E becomes equal to F over Q, force per unit charge. This is what I was explaining, that the flux lines will move away from the positively charged body towards the negatively charged body, right? And they always meet the charged surface at 90 degrees. So at the intersection, that angle should be 90 degrees. So the flux distribution between charged bodies is such that if you put a positive towards a positive, there is repulsion. So these flux lines will not intersect. And if you put a positive next to a negative, there will be attraction. And it means the flux will be net towards the negative charge. So like charges will repel and unlike charges will attract. So it means if you also add a negative and a negative, the flux will be coming into the body like that. But again, they will not meet. There will still be repulsion because of that scenario. That's what we are talking about in terms of the charges. Okay? Then we talked about flux lines representing the electric field, right? So the electric flux density will now be the flux per unit area. That is what I was explaining, that since we can represent the flux by a number of lines passing through a point, though we cannot physically enumerate them, then we are saying the flux per unit area becomes the electric flux density. And the electric flux density is equal to the charge on the body. So if you are given Q, that also becomes your flux. If you are given the charge, that becomes your flux, right? Meaning to say, in that case, the flux will be measured in coulombs, right? Electric field strength, therefore, the force acting on a unit charge at the point in an electric field. I think I explained that. Then, we were explaining the electric field because we store energy in a capacitor as an electric field. So, it means the amount of charge that you can store in a capacitor will depend also on the electric field or the flux that you can establish in the material. So a capacitor will be made up of two conducting plates, right? That's conducting plate number one, conducting plate number two, and some material in between, which we call the dielectric. So that dielectric material will be put in between them, in between your metal plates to create your capacitor, right? So if you use different dielectric materials, then it means you can also store different amounts of charge, and hence you can establish different magnitudes of flux between the two plates, right? And what characteristic makes the difference? The characteristic of the dielectric materials which makes the difference is called permittivity, right? So permittivity, in simple terms, is the measure of how easy a dielectric can permit the establishment of flux lines within the dielectric. So it simply means that if the permittivity is higher, it means you can also establish more flux within the material. It is also the ratio of flux density to the electric field intensity in the dielectric. So you can describe it in two ways. It's a measure of how easy you can establish flux lines in a dielectric, or the ratio of the flux density to the electric field intensity in a dielectric. Now you realize that in most cases, we don't quote the absolute permittivity of material, but we use what is called the relative permittivity. Right? So when we talk about relative permittivity, we are saying we have the permittivity of a material, right? Then we also have the permittivity of air or a vacuum, which will be taken as the reference. So realize that relative permittivity now becomes the ratio of the absolute permittivity of the material to the permittivity of a vacuum, right? So in other words, we are saying, call it epsilon R, relative permittivity, becomes called epsilon naught, which is the permittivity of a vacuum, over epsilon, which is the absolute permittivity. Sorry, the other way around. Relative permittivity becomes equal to the permittivity of the material over the permittivity of the vacuum, such that the actual permittivity of a material becomes equal to relative permittivity epsilon R multiplied by the permittivity of a vacuum. And this epsilon R is usually quoted as the dielectric constant, right? So permittivity, like I said, the measure of the ability of dielectric to permit establishment of electric flux in it. And the permittivity said it becomes equal to the flux density over the electric field strength in the material, given farads per meter. So if you can calculate the flux density in the electric field strength, you can also find the permittivity. But you can also use the dielectric constant in the permittivity of a vacuum, which is 8.85 times 10 to the power minus 12 farads per meter. So multiplied by the permittivity, the relative permittivity or the dielectric strength, it will give you the permittivity of that material. Don't worry about this number. If it is to be used, then it will be given. But it's also good to know that it's 8.85 times 10 to the power minus 12 farads per meter. So different materials have different dielectric constants, which is the relative permittivities, and also dielectric strength. Now, dielectric strength will be the maximum voltage that the dielectric can withstand per unit length of the material. We'll go to that at a later stage, right? So A is almost equal to the permittivity of the vacuum. That's why it's 1.00 something. So usually we use 1 there. Then the other materials, the permittivities vary just like this. The bigger the figure, the higher the permittivity, and hence the easier it is to establish flux in that material. Also here, the bigger the figure, the higher the voltage that a material can withstand before it breaks down. That is why capacitors have different voltages given. This is 15 volt, 25 volt capacitor, 50 volt capacitor. It's because of this value. If you put the voltage beyond that given value, then your capacitor will be damaged. So it is also very important to take note of the operational voltage. You don't have to know the dielectric strength, but the operational voltage will be based on the dielectric strength. So if they say 50 volt capacitor, it means you can use less than 50 volts, but if you use more than 50 volts, then you will destroy the capacitor. So a dielectric, in simple ways, one, we know that it should be an insulator. It should not be a conductor. So when the space between the two conductors of a capacitor is occupied by a dielectric, the capacitance is increased by a factor K. That is characteristic of the dielectric, and this was discovered by Faraday. Right? So with this capacitor, right, which is not charged, has its positive terminal or plate and its negative plate at that point. But then when it becomes charged, right, the dielectric material, when you say dielectric, it has two types of charges within them. So the positive sides will go towards the negative terminal, and the negative sides will go towards the positive terminal. Now this capacitor is charged. Why? Because now there's electric tension within the dielectric. Because they are what are called electric dipoles, right? You can simplify them by looking at them as if they are lobes with positive and negative. So when you exert an electric field, you are kind of orienting them such that more positives face one side and the negatives face another side, right? But then we know that everything in its natural state will be in a disorderly manner. So as it is now, when you put those dipoles in an order such that you have net negatives there and net positives there, you have created electric tension within the material, and that becomes the electric field. And so the energy is now stored due to that electric tension in the field. So this is what I was talking about. When you look at a dipole, in their natural order, there is no defined orientation, right? But when you exert an electric field, you are forcing them to orient in a certain way. So you can see that in this diagram, there are more positives oriented toward that and negatives oriented toward that. So you've used some energy to orient these dipoles. And that is the energy that is stored in the electric material, right? So when the dielectric is present in an electric field, its molecules are polarized in such a way that there is a net dipole moment parallel to the field. The net effect is the creation of a surface charge on the dielectric faces near the plates, positive here and negative there. The surface charges are called a bound charge because it is bound to the molecules of dielectrics and cannot move. So what we are saying is that you are just orienting the dielectrics, but you are not moving any charge out of that, right? And then by this way, a net electric field is in the dielectric is weakened, right? So a capacitor now, I will explain this, is constructed using two parallel conducting plates separated by an insulator. Capacitance is the measure of the capacitor's ability to store charge on its plates. This is a more refined definition. So a capacitor will have a capacitance of 1 farad if it can store 1 coulomb of charge when it is exposed to a potential difference of 1 volts, right? So we can say C is equal to charge over voltage. C is equal to Q over V. This is a very important formula to remember when dealing with our capacitors. C is equal to Q over V. So the farad is very large. That's why we have quotations of micro and picofarads and nanofarads. Nano, I'm sure you know, is 10 to the power minus 9. Because the farad, just like charge, the farad is a large value. So we have multiples of that value. Different capacitors for the same voltage across their plates will acquire greater or lesser amounts of charge in their plates, and the capacitors have greater or lesser capacitance. In other words, if you put a voltage V across the capacitor, then depending on its capacitance, it can store either Q1 or Q2. And I'm sure if you link it correctly, you realize that it is because of the use of different dielectric materials. So, when you are looking at a capacitor, in our assumption, we said all the electric flux lines are bound within the area bound by the plates. But in reality, the flux also bulge out of the common area, and this effect is what we call fringing. However, in our analysis, we will ignore fringing. We will assume fringing is negligible, right? So assume zero fringing, so that if we say the charge is Q, then all the charge is bound within this surface area. So we ignore fringing, but we should bear in mind that in reality, the flux lines are not all bound in this common area determined by the plates. But for our calculations and our determination of any quantities, we will neglect fringing in our calculations. So the dielectrics, the insulator of the capacitor, the purpose is to create an electric field to oppose the electric field set up by free charges on the parallel plates. That's why if you realize the positive terminal, we have a net negative inside the capacitor. In the negative terminal, we have a net positive in the capacitor. So it creates a field that opposes the field set up by the free charges on the parallel metallic plates, right? Dipoles are formed within the insulator of the capacitor when the electrons of the insulating material are unable to leave the parent atom and travel to the opposite plate of the capacitor. This is what I was explaining, saying they will be bound within their molecules, but they get oriented due to that electric field. So for every dielectric, there's a potential that if applied across the dielectric, it will break the bonds within the dielectric and cause it to break down and allow current to flow. This voltage is called the breakdown voltage, and then it will be an indication of the dielectric strength, right? If you remember, I was showing that in the table, which I was showing you there. So types of capacitors, we have different types of capacitors. We have fixed capacitors, which are usually mica, ceramic, electrolytic, tantalum, and polyester film, right? Then a mica capacitor, we have a mica sheet separated by the metallic foil. So in other words, you realize that in most cases, we talk about the type of capacitor based on the dielectric in most cases, the dielectric that we use, right? So electrolytic capacitors commonly used in situations where capacitance of the order of 1 to several thousand microfarads are required. Used in DC networks because they have good insulating characteristics between the plates. Basic construction consists of rolling aluminum foil coated on one side of the aluminum oxide. In other words, we have these foils there, and then the dielectric is put in between there, and there will be rolled like that. That is the construction. Well, I'm not going into details with that. Then also what are called polyester film capacitors, right? Consists of two metal foils separated by a strip of polyester material such as mylar. Outside there, the polyester is applied to act as an insulating jacket. Each metal jacket is connected to the lead that extends either axially or radially from the capacitor. The rod construction results in a large surface, and the use of the plastic dielectric results in a very thin layer between the conducting plates. The capacitor can be used for both DC and AC networks. Well, you go into details of this when you are designing your circuits and you want to see which capacitor to use. Then we also have ceramic materials used also as dielectrics, and they produce the ceramic capacitors. A very low leakage current and can be used in both DC and AC. So these are very common because they are robust. They can also retain their charge for quite long periods of time. Can store their charge for quite a long periods of time. Then there's what is called the working voltage. This is the voltage that can be applied across the capacitor for long periods of time without breaking it down. So that's why I'm saying you can have a 25 volt capacitor, a 50 volt, 100 volt, and the like. These are the working voltages. So these are the safe voltages, which if you can keep a capacitor there for some time, it will still operate well. Then the surge voltage, that the maximum voltage that they can be applied for a short period of time. That means there's a spike in voltage, there's a certain level voltage where the capacitor will not break down. That is, if it is exposed for a limited amount of time, then the capacitor will not break down under that surge voltage. Then leakage current, the current that results in the total discharge of a capacitor is the capacitor is disconnected from the charging network for a sufficient length of time. In other words, we are saying, yes, it's a dielectric material. So if we store our charge in the plates, right, positive and negative, right, some current will slowly flow from the positive to the negative within the capacitor, and that is the leakage current that we are talking about. So if your capacitor is disconnected for a certain amount of time, then this leakage voltage will slowly depreciate the charges on the plates until you have your capacitor being fully discharged. That's the leakage current. Then there are also what are called variable capacitors, right? Usually they use the A as the dielectric, and you can turn a shaft to vary the common area and hence the capacitance. So you can be turning these knobs, or you can turn this, and then you'll be changing the capacitor. These are also used whereby you are designing a circuit and you are not sure which value is exactly required. So we have to use that and adjust in the circuit. So how do we measure capacitance? You can use the digital multimeter, Then you select capacitor or capacitance. Then using these two nodes, you can also measure the capacitance to come out there. Then the next thing that we want to look at will be transients in capacitive networks. So in other words, we are saying when we expose the capacitor to a certain voltage, remember we said its voltage will not change instantaneously. Remember there is that orientation of the dipoles within the dielectric material in the setting up of the opposing electric field as we deposit charge on the conducting plates. So that will take some time, and we'll try and check and make calculation to see how long it will take to fully charge the capacitor or charge it to a certain value, and that is what we'll call transients. So as it is, this will be our next topic of discussion on Tuesday. I'm sure it will be Tuesday after lunch. That's when we start to look at transients. Right? So we'll look at transients on Tuesday onwards to see how the capacitor will respond to changes in voltage across it. So for now, this is the end. So today we've just introduced capacitors so that when we discuss them, you will know
guys, did anyone understand the part where you explained about leakage current? Can you please explain that for me? Sorry, sir, we can't hear you.
Okay, I was saying I had lost my connection. We'll continue using transients on looking at transients, that is on Tuesday. So saying transients is what happens when you change the voltage across the capacitor. Want to see how long it takes to change a capacitor to a certain value, and so on. So you just go to your notes, look at transients in capacitive networks, and that will be our next topic of discussion. Remember, in transients, we'll be looking at charging and discharging of the capacitor. What happens when you are charging the capacitor, and what happens when you are discharging the capacitor. So for now, I will end my recording now. Right. So